Good day, everyone. I am Ordejan, a BS Ceramic Engineering student at Mindanao State Iligan Institute of Technology.
Good day, I am Mitchevelle Jimenez, also currently taking up Bachelor of Science in Ceramic Engineering at Mindanao State University, Iligan Institute of Technology. Today we are going to present a video blog about the concept of Modulus of Rupture and its significance as a requirement in our class Sir 133.1 Thermal and Mechanical Properties of Ceramics Laboratory under Professor Raymond Virtudazo and Engineer Ordejan Arcasa. The content of this presentation are as follows. MOR definition, materials, flexural test standards, standard test methods, calculation of MOR, MOR significance, and machine used. One way to determine how strong a material is to measure how easy it is to break it. Modulus of rupture, frequently abbreviated as MOR, sometimes referred to as bending strength, is a measure of a specimen's strength before rupture. It is also known as flexural strength, bend strength, or fracture strength. The modulus of rupture of a material differs from its tensile strength in that it defines the maximum stress that a material can withstand before undergoing severe deformation due to stretching. The two properties are intrinsically linked. When a component or test piece is tested under 3-point bend conditions, the concave surface is subject to compression, while the convex surface elongates under tension as shown in Figure 1, eventually leading to rupture or failure of the component. Typical materials. Polymers are most commonly tested with a 3-point bend test. Specimen deflection is usually measured by the crosshead position, and the test results include flexural strength and flexural modulus. Wood and composites are most commonly tested with a 4-point bend test. The 4-point test requires a deflectometer to accurately measure specimen deflection at the center of the support span. Test results include flexural strength and flexural modulus. When a 3-point bend test is done on a brittle material like ceramic or concrete, flexural strength is often called modulus of rupture. This test provides flex strength data only, not stiffness. The 4-point test can also be used on brittle materials, though alignment of the support and loading anvils is critical in these cases, and the text fixture for these materials usually has self-aligning anvils. Common ASTM and ISO flexural test standards. ASTM D790 standard test methods for flexural properties of unreinforced and reinforced plastics and electrical insulating materials. ISO 178 plastic determination of flexural properties. ASTM A370 tensile testing and bend testing steel reinforced bar.
So now let's proceed to MOR standards test methods. In order to test the flexural strength of a material, for example, a concrete beam, its span length should be at least 3 times the depth. The flexural strength is expressed as the modulus of rupture MR and PSI megapascals. There are two standard test methods to determine the flexural strength of a concrete beam. First, center point loading test. As shown in Figure 2, the entire load is applied at the center of the beam span length in this test process. The flexural intensity or modulus of rupture is higher here than it is in the third point loading test. The second standard test methods to determine the flexural strength of a concrete beam is the third point loading test or the 3-point bending test. As shown in Figure 3, half the load is applied at each third of the beam's span length in this test process. The flexural strength or modulus of rupture measured here is lower than that measured in the center point loading test. The highest stress is found in the center one-third of the beam. The modulus of rupture, determined by third point loading, is usually 15% lower than the modulus of rupture, determined by the center point loading. And now, let's proceed to the calculations of modulus of rupture. The formula for modulus of rupture differs for different types of loading system. For the first equation, it is for a rectangular sample under a load in a 3-point bending setup, in which sigma equals 3FL all over 2BD squared, where F is the load or the force at the fracture point, L is the length of the support span, B is the width, D is the thickness. For a rectangular sample under a load in a 4-point bending setup where the loading span is 1/3 of the support span, equation 2 will be used. Sigma equals FL all over BD squared, where F is the load or the force at the fracture point, L is the length of the support or the outer span, B is the width, D is the thickness. For the 4-point bending setup, if the loading span is 1/2 of the support span, equation 3 will be used. Sigma equals 3FL all over 4BD squared. Next, if the loading span is neither 1/3 nor 1/2 the support span for the 4-point bending setup, equation 4 will be used. Sigma equals 3F open parenthesis L minus L sub I close parenthesis divided by 2BD squared, where L sub I is the length of the loading in the inner span. So why is it important to calculate the modulus of rupture of a material? Engineers would like to know about different aspects of a material's nature, but the simple uniaxial tension or compression test cannot provide all the details you need. Tension, compression, and shear forces are all applied to the specimen when it bends or flexes. As a result, bend testing, or MOR, is often used to assess how materials react to practical loading. For example, a plastic chair needs to give support in many directions. While the legs are in compression when in use, the seat will need to withstand flexural forces applied from the person seated. Not only do manufacturers want to provide a product that can hold expected loads, the material also needs to return to its original shape if any bending occurs. On the other hand, in structural mechanics, calculating the modulus of rupture is important as elaborated by Raymond. First, it helps in designing structural elements like beams, cantilevers, shafts, and etc. It aids in the study of materials and their properties. It provides a parameter for development of stronger constructional materials. Flexural strength helps in judging the quality of structures being used for construction. Lastly, it is a tool to predict both resistance and durability of objects. MOR, sometimes called flexural testing or transverse beam testing, measures the behavior of materials subjected to simple beam loading. It is commonly performed on relatively flexible materials such as polymers, wood, and composites as mentioned earlier. At its most basic level, a bend test is performed in a versatile testing machine by placing a specimen onto support anvils and bending it through applied force on one or two loading anvils in order to measure its properties.